Hello, everyone, to our discussion today regarding mechanical reliability for electronics. My name is Thomas. I'm with Namratha is here as well. She's an application engineer here at Leap Australia and focusing on reliability assessment for electronics. We're both part of the electromagnetics team, and the plan for that webinar is a little bit, I will talk for 10-15 minutes on the challenges, the problems, and also the solution. And then as the core in that webinar, we will have Namratha showing a little bit the solution, showing you the GUI and showing you also the workflow that is related to that. So the topic is really important for not just PCB designers, but also for analysts or product and project managers. Electronics are usually getting more and more complex these days. We all know that they're getting also smaller, and they are expected to have an increased reliability. Sometimes we even need to have a higher reliability across a longer life, service life. So it doesn't always need to lead to those catastrophic failures here, as you can see with the airplane crash. But reliability is really a topic where product success is depending on not just making a good product and designing it, but also then across its lifespan, having the product being successful and costing not much for the company or the one who is developing it. When we say reliability, we mean electronics reliability, but also mechanical reliability. And electronics reliability can, of course, be related to EMI and EMC issues. We don't touch much on that today. We will have a look at electronics reliability in a sense of wear out and those things. But the main focus will be on thermal aspects, vibrational aspects, and so on. This is a little bit to categorize everything. We have mainly three failure causes, and they can be shock and impact related. We have also vibrational induced failures or thermal induced failures. You can see on the bottom a couple of simple examples where we have, for example, a displacement on our board, and then we see higher stresses and strains that then can lead to a failure. There's also component resonance that can be critical, especially for very, very heavy components on our board. And then on the left side, you can see a very simple CTE mismatch problem where we have basically an electronics package soldered to a PCB. And once our temperature is going beyond the neutral temperature, the board will be expanding, and then the solder joints, of course, see stresses and strains. And if the other way around, we get a lower temperature, the board will contract, and then we see the joints stretching on that side as well. So this is just a couple of basic physics that are related to those topics and that we would like to be prevent, but at least being able to understand and to assess. What we have done here is outlining a little bit of the standard development process that people take these days on build and test with physical prototypes. So you start to design your PCB, you build a prototype, and then you test. For the test, we take the EMC and EMI topics out, but you can see on the bottom, I put a little test plan together that I got from aerospace electronic applications. And you can see the different categories. You can also see a couple of standards, and you can see what time it takes to test those things. And you can, yeah, in that column, you can see some of the time is 57 hours for a thermal test, or even 5,000 hours for component failures. This is really just the reported time the test takes. It doesn't mean that it has been spent on the setup or on getting the test underway. People can these days shortening those tests for some. So sometimes people build a couple of PCBs and then do tests in parallel. There are also other acceleration methods. For example, if you want to test your product with one cycle each day and then over 1,000 days, you could easily take a 15 minutes ramp and then a 15 minutes dwell and realize the test for up to 24 cycles a day and then shorten the time on that. But even that will still take days for us to do those tests. And let's not forget, in that loop, if we come up and fail that test, we have to do everything again. We have to build prototypes again and then run through those tests as well again. So simulation has been used to accelerate and to aid those, and that should be a good way forward to improve those design processes. We will later have a look at where we can in detail apply those, so during the design, but also definitely after the design and then before the physical prototype and build a stage, we could definitely do a simulation to get an early understanding on what could be wrong to improve the board before we go and make a prototype. So when we move into the simulation space, we traditionally had always a couple of challenges with modeling PCBs. If you look at, for example, ECAD data, rather they're coming from Altium or from any other ECAD package, it only represents the layer stack up. It gives us the traces, it gives us the vias, and the pad sticks, but it doesn't give us anything beyond that point. So we don't really get the solder balls, we don't really get the leads or the wires connected to our components. And on the other side, sometimes the ECAD packages are producing also MCAD data that can then be used to represent the component, but that is in most cases only just a block of the semiconductor, but is also not including the solder and is also not including the leads. And then there are some additional challenges. For example, if you want to have some potting in place, that is also difficult to implement. And then on the material complexity, of course, we want to have a look at crack, we want to have a look at creep, and we want to account for different physics. So stresses should be dependent on what temperature we are looking at in our PCB. So those analysis and simulations are not trivial, and we need to, if we want to get good answers, take all those things into account. The second aspect of it is that simulations traditionally only give us displacement, stresses, and strains, and we cannot really get a good understanding from that. Okay, we have the stress and the displacement, but how long will the product survive in the field for a given environment and for given loadings? So what we need to apply, of course, as well as reliability physics analysis, and there's lots of research in papers and documents and books where people building and creating equations based on tests and measurements that are then able to understand what is my stress and then converting that stress into a life cycle prediction. So that's beyond the modeling, that's the second aspect we need to have a look at. And we have that workflow now in place. And I can just quickly outline that workflow and show you a little bit about it before Namratha later on takes over. So we can quickly import ECAD data that can come from anywhere. I think ODB is very popular. It comes from Altium, but it also can is supported by Cadence or Zuken. After that, we have a solution where we have templates or dialogues where you can put your profiles in. Doesn't need to be a thermal profile like in this picture, but can also be a shock or a vibration profile, a PSD, for example. The second aspect is that we can now understand from importing our ECAD data but also our BOM it understands the components, and we can update and get a feedback from a really large library of different components, and then bring those leads and bring those solder balls in as well. In the second step, we have then the FEA model. So push a button, get the mesh. Automatically, of course, user can have an impact on to refine that mesh a little bit. And then in the end, getting results that are really showing the risk and the life cycle for each of those disciplines, but also the overall combined risk for your module. So let's have a look before I hand over to Namratha, what is possible in terms of physics and analysis types. And the first one is the solder fatigue analysis. That is an analysis where we can take, for example, the lead length, the size of solder, the CT of the packages, and also the stiffness of the board into account to understand what solder ball will crack or not and when. The second category is mainly our vibrational, rather than it's harmonic or random for high cycle fatigue, but also mechanical shock. So the ability to add a shock profile into the environment and then to see and understand what happens with my structure if it's exposed to a shock. Then we have plated through-hole fatigue included. That also takes into account the thickness of the board, the copper thickness, the via plating, and also the quality of the vias, and also the contraction and the expansion of our PCB. Thermal mechanical, that is a classical CTE mismatch analysis. IC aging and wear out, very, very important as complexity arises and more ICs are used. Where we usually have, or we have an analysis based on all four main failure mechanisms on ICs. So for example, we have included hot carrier injection or bias temperature instability. So all those transistor level mechanisms are included to understand how long can an IC withstand, what's the wear out mechanism, and so on. Then we have the capacitors. We can have a look at capacitors. The electrolytes on one side. I think we all know that with higher temperature, electrolyte evaporates faster. So that can happen with higher temperatures. And then also on the ceramic wear out, where we have a degradation in insulating resistance that could lead to failures as well. And then the last point is CAF, which is basically a migration of copper filaments that leads to a loss of insulation resistance. So an electrochemical corrosion process that creates shorts, and this actually can really lead to very, very catastrophic failures in a PCB, and is getting more and more common. On top, there's a possible to do design FMEAs. So I mean, if we know now we have the information from our components, and if we then feed the technology with the failure rate classes from a third-party tool, we could merge that together and then have a look at the component-based design FMEA, which is very, very valuable as well.